Good morning, everyone. My name is Deanna Moya. This is Santiago, Nino, and Nicolas Polignan, and we will be presenting the automated bulk bag filler for Titan America. This is a quick project overview of what we will be getting into details today. First, our motivation for this project is associated to Titan America, who sponsored our project, but also in general to all mining companies, because it is seen that the production and distribution of aggregates using bulk bags is a very unprofitable process. Our solution to this issue, and therefore our project objective, is to design, simulate, test, and build an automated filling structure that would improve Titan's profits by doubling their production rate. As you can see here in this lower corner, this is our SolidWorks final design model, and in this chart here to your right, it shows the success of our project. As you can see, not only did we pass our goal, but we saw an improvement of 82% to their current method. So why this project? Currently, there's no mass production process for the filling of bulk bags. This process is done completely manual with shovels and this front-end loader. This process is unsafe, inaccurate, and very unprofitable. We see issues such as wasted time, wasted material, and unnecessary labor. So as you can see in this chart below, it currently takes Titan America an average of 1 hour to fill 10 bulk bags. And again, to improve profits, our project goal was to double their production rate, so 20 bulk bags per hour.
So what are aggregates? Aggregates is the most mined materials around the world. We can see aggregates on is used for any type of construction, like a building, the streets, the roads, and its aggregates include sand, gravel, and crushed stones. So one of the ways to transport and store aggregates is in flexible bulk, intermediate bulk containers, most known as bulk bags. These bulk bags have made of woven polypropylene in order to be rip resistant. These bags have an average weight between 5 to 7 pounds itself and a load resistive factor of 1,000 to 4,000 pounds. Titan America at the moment use these bags of 35 by 35 by 54 inches for about 38 cubic feet for a body. And also Titan America requests and sold the product of a weight of 3,000 pounds. So Titan America has a lot of location around the east coast of the United States, and the implementation of the automated bulk bag filler, they increase the profit around the country, and as well they allow Titan America to be a global distributor of aggregates. So these three pictures show our conceptual ideas. After we, like Deanna explained, this is our final design of the proposal design that includes all the parts that we present to Titan America.
So in order to understand what our final design looked like, I'm going to break it down into 3 components. Our first component is the hopper. The hopper has an overall dimension of 14 feet by 14 feet by 6 feet in height. This is the top dimension, and it has a total volume of 23.3 cubic yards. This hopper was reinforced with ribs in order to ensure rigidity of the hopper. Inside the hopper, we designed this cross-section that is 10 feet by 3 feet by 2 feet high. This cross-section allowed for the material to be evenly distributed through all 4 gates. So when the loader loads the material right in the middle, it makes sure that every bag has the same amount of material. Now, in order to fill this one hopper, it would take 3 buckets of the WA500 Komatsu front-end loader that we use. With 1 full hopper, we were able to fill an average of 70 to 20 bulk bags, which was one of the goals set by Titan. The next section that I want to speak about is the overall structure. Now, there's 3 main components that I want to speak to about the structure that made it unique and reinforced. The first is a cross-section that you see there. This cross-section allowed for the hopper to actually sit on there and support most of the weight when the material is set on top of it. The next part that I want to speak about is these cross-section members and connector plates and angles that help form a triangle structure and also for the weight to be distributed when the hopper is full. The last component that I want to speak to you about is the piston brace. This brace was designed and done in order to make sure that the piston opened up as required in order to fill the bulk bag appropriate. So the length of the brace itself from beginning to end was measured to make sure that the opening is not too large for the bag. The next component is the gate itself. It's a half moon shaped gate that is 2 feet by 2 feet by 1 foot high and has a degree of 70 degrees. This degree was chosen specifically to reduce the flow of material from a 60 degree to a 7 degree, so the material does not hit the scales or break anything. The next component is the piston. This piston was chosen for 2 reasons. One is the pull force that we calculated which is 17,000 pounds. This pull force was calculated to make sure that when all the weight of the material was sitting on the half moon, it would be able to open and close without any problems. The second reason we chose this piston is a piston that is commonly used around the plant, which makes sure that if it breaks, we have easy access to replace it, and also we can buy the mass quantities to reduce cost.
Once our designs were established, we performed simulations for each individual component and for components in assembly. This was done to make sure that each component design would perform under what it's exposed to. As you can see, we will show only simulations for the hopper and the structure because we determined these would be the most important, but all other simulations you can find in our report. In this top figure is the setup of our hopper simulation. The upper outer rim of the hopper was fixed because that's where it's attached to the structure. And we used a distributed load of 60,000 pounds on all of the inner faces of the hopper. 60,000 pounds was used because it was determined to be a conservative load for worst case scenario, which would be when the hopper would be full. And we used gravity denoted by the red arrow. The results that we found was a maximum displacement of 0.5 millimeters and a minimum factor of safety of 4.4. Our next simulation was of the structure. One thing I want to note is that this structure is of a previous design that we had submitted and was approved by Titan. All of the improvements and extra features that Nicolas had mentioned were added during production. However, for this simulation, it was set up similar to the hopper with a distributed load of 60,000 pounds, and the results we found was a maximum displacement of 0.01 millimeters and a factor of safety of 5. All of the components that we simulated had factors of safety well above the required 2, and therefore were determined to be a safe design by us team members and Titan engineers. Our next step was the prototype. As you can see here on the table, this prototype was built for the purpose of testing the flow of material in order to get a better idea of the impact that this structure design will have on the production rate. This prototype was built on a scale of 1:1 feet 2 inches and was made of balsa wood. The material that we used was taken from Titan's plant, and these cups that we used represent the bulk bags. In the table below, you can see the comparisons. Again, the current method, 10 bulk bags per hour. Our goal was to double the production rate, so 20 bulk bags per hour. And through several trials of experiments, we found an average of 56 bulk bags per hour. So with this design, that is a 82% improvement to the current method and a 64% improvement to what our goal was set. With these results and the simulation results, they were all presented and approved by Titan. And due to the promising results, we were given the budget and approved for full-scale production.
This is a short clip with a time lapse of how our project was developed from beginning to end. We begin by constructing the hopper and the 4 walls, uniting them. Once the 4 walls were in place, we designed and measured out the cross section and installed that. Once that was done, we decided to put the ribs all around. The next step was to make the structure. The structure was done after the hopper to make sure that the dimensions were exactly and the hopper fit exactly to the structure. Then while those two were being done, we decided to make the gates. The gates were done very efficiently in a way of mass production. Since all 4 gates were exactly the same dimensions, they were cut, each piece was cut in the same manner. So the same side was cut 16 times because we only had 4 gates. Once that was done, it was all placed and painted and tested.
So, as Nico explained, so after all the production process, this is our full scale model that includes all the importance and the main components that are the structure, the hopper, the chutes and the gates, and the piston. So the standards, three main reasons for the standard there is safe cost, comparability, and safe operation. For welding, it's really important to follow the standards of the American Welding Society in order to make sure that the proper unification of the material and the proper safe of the operators. Another important thing is the comparison there is in order if Titan requests to, or if they needed to replicate the automated pullback filler, it's really easy to do it because they already have all the standards. And for example, as well, another standard I use is like the bolts, the angles, and the steel plate dimensions.
Now, I want to talk a little bit about our budget. Initially, the company gave us a budget of $37,000. We ended up spending about $33,300, which means we had a total saving of $3,600. This is a total of 10% saving. Now, how do we achieve this savings? Well, we used 2 things. One was bidding. For things such as the scales and pistons that we bought from and not manufactured, we went out and contacted at least 5 or 6 different companies and requested different quotes. After analyzing each quote and what they were offering, we decided to choose the cheapest and most reliable object. The next one was manufacturability. We made sure that all the material was used, such as if we were going to cut a steel plate to make one of the hopper walls, we made sure that the rest of the material was used to 100% and none was wasted. Also, we made sure that all our dimensions were standard and there was no unique dimension or anything that would have to be manufactured outside of the company. Also, this graph shows where our costs went to. As you can see, most of our costs went to labor and materials. Finally, what is the next step? The next step for our structure is to be placed in a location within Titan that is both beneficial in forms of efficiency and cost to make sure that it is near all the stockpiles that will be loaded to the structure. The next one is also to run pneumatic lines and also electricity for the scales. Finally, and future work will be to add a PLC system that will allow the gates to shut off by themselves when the weight reaches 3,000 pounds. Before we go, we want to thank everybody at Titan, especially Ruben Terrazas, which is the plant manager, for giving us the opportunity to work with a real budget and a real problem. Also, we want to thank Juan Reserva, which is the loader aggregates supervisor, which had a lot of feed in on where to put it and how to design it. And finally, we want to thank all the welding team for all their hard work and all their input. Thank you.
Any questions?
Okay.
Thank you. Have you fired this up and actually filled some bags with it now? And
Also, like Nico had mentioned, we have to move the final structure into its location where the Titan wants it and run the electricity lines. But once that's done, assuming it goes through a process of safety and then
Yeah, there's since mining sites are regulated by MSHA, they require certain paperwork to, like, if you're gonna establish a new routine, you gotta fill out whole paperwork and have what's called STA, safety tax assessments. And once we fill that out and have that form, it should be ready to be done once we run, like she said, electricities and airlines.
So when all that is done, are you gonna, the three of you gonna go over and push the button and see if everything
Yeah,
works?
well, I work there, so
Oh,
I'm gonna have to finish the project. They're gonna be behind me to finish it.
Question I want to ask, is this system bolted down?
No, this structure, one of the design constraints that we worked with was making it mobile.
Okay, so the next question I have to ask you is that you assumed a distributed load would be applied of all 60,000 pounds would be basically distributed across the whole structure. But the reality is that you're going to be coming up to it with a tractor. You're going to be loading into one side. So it's not necessarily going to be distributed per se. So the question I'm asking basically is the system stable so it won't flip over when they put the 60,000 pounds on one side?
Correct is what she said. Even though it is mobile, it's going to be set on a slab. Once it's a slab, it's going to have rebars going up and attached to the frame itself. So for as far as rigidity, the four pillars are going to be set on concrete, but in a way that you could take them out if required to. All you have to do is pour a new slab.
Okay, good. Thank you. Your 82% improvement, that was executed on the prototype system?
Correct.
Yes.
Okay. Did you do any additional stress analysis work when you added the ribbing around the design to prove what that benefit was?
Additional simulations weren't run because they were already approved in its initial state. The ribs were added during production, so it would be interesting to see the improvement in factor of safety and stress, but we did not run.
So you don't really know if the complete design is safe per se because you didn't actually do the analysis.
Well, like she said, since it was the way it was set, those grids were added during manufacturing based on all the hoppers that are available within the plant, and they work in the plant, and it shows that they last longer with the ribs. So that's why it was chosen during manufacturing.
Okay. And then has there been any testing done on the full-scale system?
No, because like I said, we can't physically test it until the form is done. We can't do that until it's 100% done, which should be within a month. We should be able to get the slab poured, and I already have the scales, everything bought. I just have to pour the slab, connect the lines, and test it out.
Thank you.
The application that you did, is that something from a governmental agency or like a requirement for OSHA or?
What do you mean application?
Well, you just said you had to fill out some forms before
It's
this.
MSHA. MSHA is like the OSHA OSHA is for any work agency. MSHA is the mining safety committee. They're a lot stricter than OSHA. They get mine sites gets audited twice a year, every year, and those safety tracks things are reviewed by those inspectors. So let's say if somebody's working on there and they didn't fill an STA that day, the mine could be shut down until legal matters.
So once you do this application, does an inspector come out and
No.
check out?
No, it's in case they do, when do come out and they say, wait, did you do an STA for this machine? And then we have to present the paperwork, but you don't have to physically submit it.
So you don't need a license or anything like that to be able to do that?
Is there any plan for potentially put light guards or anything on the system to guarantee that people can't get underneath them at the same time that the gates flip open?
Once we were set it into place, we will see what's the optimal way to load the material and to provide safety, because it is an open area where the mine site is a very open area. So we could make barriers around.
Well, and what I'm suggesting we use is a light guard. So basically, if something goes through it, it acknowledges and it would give you the ability to disable
Right.
the ability for the gates open.
it's something we could look into. The only problem is, if maybe if something does fall over, like while loading, it could trigger that and cause problems, but it's something we could look into.
Would they ever load this with I know as I drive down the interstate, I look and I see this big long conveyor that goes under the road.
Yeah,
Would they ever consider having a conveyor come up to the top and load this by conveyor rather than a front loader?
if production is large enough that you would need that quantity to be constantly producing, then they would implement a belt. But since production, you don't load 24 hours bags, it's per shipment, not a daily thing. So most of these are sent out of the country. So it would be more cost effective for now for front-end loader. But if mass production is needed, they would implement a structure where you need a conveyor belt.
So if somebody orders 1,000 bags, you fill 1,000 bags, you put it on trucks, it gets shipped, and then you might not do it again until you get another order for it.
Or the second option is to keep in a stock. So maybe not 1,000, maybe 200 bags of certain material. But the problem is that Titan produces a large quantity of different materials, so keeping that amount of stockpile can be expensive because of land.
Okay, thank you very much.